Okay, so our next topic is called simple harmonic motion, sometimes abbreviated SHM. All right, so simple harmonic motion is a special type of oscillation. There's many ways in which something could oscillate back and forth. There's many different mathematical descriptions for the way in which something could oscillate back and forth. But in the most simple of cases, something special happens, and that's what we're going to describe mathematically in this section. All right, so what is special about simple harmonic motion is that as something oscillates back and forth, that oscillation does not depend on the amplitude. Right? So I could have this glider on the spring on a massless table maybe, and I could compress that spring half a meter, and this object would oscillate back and forth with some period and some frequency, maybe twice per second or something like that, right? Or I could take that same glider and I could compress it instead of half a meter, I could compress it a whole meter, right? It turns out when you do this with simple harmonic motion, this glider, although it's traveling a further distance, it's traveling from -1 meter to 1 meter to -1 meter to 1 meter, as compared to this one, which is traveling from minus half a meter to plus half a meter back and forth. Right? It turns out they both take exactly the same amount of time to go through one oscillation. They have the same period. All right, so that's a very special case. And for that reason, we call it simple harmonic motion. Simple because it's a little bit more easy to describe mathematically. Harmonic because it's related to how you wanted to design an instrument, right? When you have a guitar string, or in this case a piano string, you don't want the sound that that makes to be related to how hard you hit it, to the amplitude, right? So with a piano, if you touch the key lightly and the hammer kind of hits the string very lightly, you get an oscillation back and forth at some frequency. If you hit the same key really hard and the hammer hits that string really hard, you get the same note. Right, you get the same frequency of sound coming out, and that's what you want to happen. The same thing with the guitar string or any other instrument. So that's why the word harmonic is included in here. Simple harmonic motion. Okay, so how does simple harmonic motion happen? Simple harmonic motion occurs when the restoring force is directly proportional to the displacement from equilibrium. Right? So we know that for a spring, the force that a spring exerts on an object is equal to minus kx. It's called Hooke's law. We've seen it before, right? This is the restoring force. It's equal to minus k, where k is a spring constant or the force constant, right? So k is some number that describes kind of how strong that spring is, right? The stronger the spring, the bigger that spring constant or the force constant. And x is our displacement. How far away have we displaced that spring from equilibrium point? So this is our restoring force, and we've already seen that when you have a positive displacement, when x is positive, you have a negative force. And when you have negative displacement, you have a positive force. And that's what you need for an oscillation. You have a restoring force. And in the special case where this is linear, just like this, where x is not squared, it's not cubed, right? It's just this is a linear relationship. In that special case, we get what's called simple harmonic motion. Right? So if I was to plot force versus displacement, again, if I'm at equilibrium, I have zero displacement, there is zero force from a spring. If I have a positive force, if I have positive displacement, that means a negative force, right? Negative force. If I have a negative displacement, I have positive force. And this relationship is linear, where if I double my displacement, I double my restoring force, right? So that's a special thing you need for simple harmonic motion. And we'll derive this equation shortly, but this is we can quickly discover that this is the equation for simple harmonic motion, because force is equal to mass times acceleration, and acceleration is just the second derivative of position, right? So the special case that you can derive with simple harmonic motion is that the acceleration is related to the position, okay? If I have a large positive displacement, I have a large negative acceleration. Right, so that's a special thing that's going to happen here. And we'll see more about this in a moment. When do you not get simple harmonic motion? Well, a lot of forces aren't this nice. Right? You could have a force that's not linear, where if I displace some object 1 meter, I have some amount of force, but if I displace it 2 meters, I don't have double the force. Right? Maybe I have 50% more force. So in this case, right, I do not have simple harmonic motion in this red line. And it's going to be a little bit more complicated to describe that mathematically. So you can imagine a lot of the objects oscillate. If it's a small oscillation, if you're just a small amount of displacement, a lot of objects do exhibit simple harmonic motion. But at some point, if you overstretch a spring and you permanently deform that spring, for example, you're not going to get simple harmonic motion anymore. Or there's many other examples where you don't get this nice linear line where you deviate from that. But still, for small oscillations, small displacements, simple harmonic motion describes a lot of things we experience in everyday life, from musical instruments to tuning forks to the alternating current coming out of the sockets in your house, to atoms oscillating back and forth or molecules oscillating back and forth, things like atomic clocks. All of these things exhibit simple harmonic motion. So let's talk a little bit more about simple harmonic motion. And again, let's just apply Newton's second law. We know that the net force of an object is equal to mass times acceleration. In the x direction, there's only one force affecting this glider, and that's the force of the spring. So I can replace my net force with my equation for the force of a spring, minus kx, where k is a spring constant. And I have this very simple relationship, minus kx equal mass times acceleration. And I can just solve this for acceleration, and I get that acceleration is equal to minus this constant, k, divided by the mass times displacement. Right, so the acceleration of this object is going to be directly related to its displacement. The more positive the displacement, the more negative the acceleration. If I have zero displacement, if I'm at equilibrium, I have zero acceleration. Okay, so acceleration and displacement always have opposite signs. And that's what we have for a restoring force. Positive displacement means a restoring force pushing you in the minus x direction, which means you have negative acceleration. Okay, so let's rewrite this formula. I know that acceleration is just the second derivative of position. So I just take this formula and rewrite a as the second derivative of position. And what we see is maybe a little bit scarier looking, but this is a differential equation. You may not have seen this in math yet, and that's okay. We're just going to try to understand it because this is a pretty simple example. What is special here is if we wanted to describe the position with some function, the position of this glider as it bounces back and forth, how could we do that? Well, I need to pick some equation for this position where if I take two derivatives of it, I get the same thing back, okay, plus some extra constants and a negative sign. So that's a pretty special type of equation. What kind of equation could I plug in for x that I could take two derivatives of it and get the same thing back? Okay, so we're going to talk about this in multiple ways. One is a little bit more mathematical, and the second way is more of something you can picture. So the mathematical way of solving this is, again, here's our equation. This is what Newton's law told us, that the second derivative of position is related to position. Okay, so I need to come up with some equation for x to describe at any moment in time what is the position of this this glider. We want to find the equation of motion. Just like we found before for a projectile, the equation of motion as a function of time, we want to do the same thing here for this glider oscillating back and forth. So I'm going to first just guess a solution. I'm going to guess that if I replaced x with a cosine that depended on time, that maybe that would satisfy this equation. So we're going to basically solve this by guessing and checking. We're going to guess that this is a solution and then plug it in and see if it works. And I think cosine may be a good guess, right? Because cosine, number one, looks like an oscillator, right? If you plot cosine as a function of time, it looks like something oscillating back and forth. So that should be leading us in the right direction. And the other thing is that I know that cosine does something special. When I take a derivative of cosine, I get negative sine. Right? When I take a derivative of sine, I get cosine. So if I take two derivatives of this equation, I get this, right? Which is basically minus k over m times cosine square root of k over m times t. And this term, cosine square root of k over m times t, is just my original equation for x. So I can replace this with x. And I can show that this worked. When I take two derivatives of this function as a function of time, I get the same function back. Right? I get cosine back again, except this time I have a minus sign out in front and some constants have popped out. Okay, so that seems to work, and so cosine is going to be a good guess for what is the solution for this equation and what equation is going to describe this type of motion. Okay, the other way we can think about this is a little bit more something we can picture. Excuse me. And what we're actually going to do is relate simple harmonic motion and circular motion. Okay, so if you remember uniform circular motion, we have an object on a turntable, like a record player or something like that, which is spinning, right? It has some angular velocity. It's moving through some number of radians per second, and it's spinning at a constant angular velocity. Okay, so this ball is going to spin around. Right? I have this turntable. I've placed this ball on the edge of the turntable. That ball is going to just spin around at a constant rate. But if I look at just one direction, for example, just look in X, this ball is going to appear to be oscillating back and forth. In fact, if I had a light beam and I just shined it on this turntable, I would see the shadow of this ball on the wall just oscillating back and forth. The shadow would just be oscillating between some maximum position and some minimum position. Right? So that would look a lot like an oscillator. Okay, so if I kind of look at just one dimension of the two-dimensional circular motion, that one dimension looks exactly like mathematically what this oscillator is going to be like. Okay, so we can make this analogy. We can define what we call the reference circle and describe the motion of this ball as a projection of this reference circle, right? But the projection is this light is shining on that ball and projecting this shadow onto the wall. So we're going to call this rotating vector a phasor, and just note that as this ball spins around in a circle, if I just look at the x component of its position, all right, the x component is given by a cosine, and that position is just going to be oscillating back and forth. Excuse me again. And this is something you can use in engineering to design something to move back and forth. This is called the Scotch yoke. You can have something that moves in a circle that just moves something back and forth. Okay, and so this is kind of the analogy we're going to make, is that something moving in a circle can also describe something oscillating back and forth. Okay, so if the x position of this object is oscillating back and forth, and we can describe its position with a cosine, we can also show that the velocity vector, right, at this moment this ball has velocity in this direction, that velocity has an x component. The x component is actually given by minus sine, and this ball at this moment also has acceleration toward the center of the circle. We know that anything moving in uniform circular motion is always accelerating towards the center of the circle, keeping it going in a circle. This acceleration vector also has an x component, which is defined by negative cosine. So this is exactly what we want to describe something oscillating back and forth. Okay, so we're going to continue using this kind of analogy of something moving in a circle to describe something oscillating back and forth, something not moving in a circle. In fact, we're going to use some of the same symbols, so this may get slightly confusing, but we're going to define something called the angular frequency omega, and I'm going to use the same symbol omega as we used for the angular velocity of something moving in a circle. Right? Because we're making this analogy, it turns out these are very related. We'll talk more about that later. So we're going to define angular frequency omega. It's going to be equal to 2 pi times the frequency. Right? This is just number of cycles per second, and I know that frequency is just 1 over the period, so that also means the angular frequency is related to 2 pi over the period. Okay, so frequency is the number of cycles per second, right? It's the unit of hertz, or cycles per second. But if I multiply that by 2 pi radians, angular frequency is radians per second. So it's how many radians per second is that object on the reference circle moving through, right? To help describe how that shadow is moving back and forth. And it turns out that the angular frequency is related to the properties of the thing that is oscillating. So for a spring, the angular frequency is related to the spring constant and the mass. Right? We already have seen this square root of k over m pop up a few slides ago. Right? If I have square root of k over m, if I take two derivatives of it, I get the same thing back. So I get that equation we started with. Right? So it turns out that if I want to describe the motion of something, one of these springs oscillating back and forth, the frequency at which it oscillates is going to depend on the spring constant. A bigger spring constant is going to be a bigger restoring force, and it's going to oscillate faster. It's also going to depend inversely on the mass. A bigger mass is going to have a smaller frequency. A smaller mass is going to have a bigger frequency, as you may expect. Right? So angular frequency and frequency are closely related. They just differ by 2 pi. Right? So if I want to define frequency, it's just 1 over 2 pi times the square root of k over m. And period and frequency are also very related. So I can write down the equation for period as just 1 over the frequency. So the period of the spring oscillating back and forth is 2 pi times the square root of m over k. Right? A more massive object is going to have a larger period. It's going to take longer to complete one oscillation. An object with a bigger spring constant is going to have a shorter period. Right? This is in the denominator. A bigger spring constant means a bigger restoring force and a smaller period. Okay, and we'll quickly note that the period does not depend on amplitude at all. Right? So if I stretch the spring out 1 meter or 2 meters, it doesn't matter. It's going to oscillate at the same rate. Okay, it depends only on the mass and the spring constant. So we have simple harmonic motion. That's really nice. And so I'm going to just quickly show a couple of nice videos to demonstrate simple harmonic motion and how we're going to describe it mathematically. So let me get the videos up here. Okay. In this first case, we have a pendulum filled with sand over a treadmill. So the pendulum is just going to oscillate back and forth, but as it drops sand, it's going to you're going to be able to picture the position of the pendulum as a function of time. Okay, so the pendulum is just oscillating back and forth, but look at the sand. The sand is also just oscillating back and forth, but by putting it above this treadmill, we're kind of seeing as a function of time the position of that sand. Right? So it looks to be something like a cosine or sine curve. Okay, so that's our first nice little picture of describing simple harmonic motion and kind of proving to ourselves that a cosine or sine is going to be a good solution. The next example is a spray paint can attached to springs. So the spray paint can is just going to oscillate up and down, up and down, up and down. It's going to have no side-to-side movement. But by again putting kind of this paper treadmill behind it, this moving paper, we're going to again see a sine or cosine appear. Okay. Let me skip forward a little bit here for you. Okay, so this spring is oscillating up and down, and you can see as a function of time, the position of that spring is just moving up and down as described by a sine or cosine. So that's a really nice another example. And we can also do this with simulation. If we look at a spring, a mass hanging from a spring which is oscillating up and down, if I just plot the position, its displacement as a function of time, it looks exactly like, in this case, a sine, right? And I can also describe its position as being the y, in this case, the y position of this object moving in a circle. Right? So there's two different ways I could describe this motion. In either case, it would be described as a sine or a cosine. All right, so that's a really nice simulation. And the net effect is simple harmonic motion, where hopefully the oscillation of the two objects does not depend on amplitude. So if I try to start this one oscillating slowly, and maybe I can actually slow this down. So I'm going to try to let this one go exactly when this one reaches its highest point. Okay, there we go. So these are oscillating back and forth, and you can see that even though this one's traveling a lot farther, it's taking exactly the same amount of time as this one to go through a complete cycle. Okay, I think I've got it pretty much dead on there. So they're both taking exactly the same amount of time to go through one complete cycle. They both have the same period, the same frequency. Right? Even though this one's traveling a lot further, since we stretched out the spring a lot more, the force is a lot bigger, so it has a lot more acceleration. It's going a lot faster as it passes through equilibrium. Right? I think I can even draw in the velocity. This one's going a lot faster as it passes through equilibrium, so that means it's able to travel this further distance in the same amount of time. Right? So these have exactly the same period, and we can plot their velocity in green, their acceleration in yellow, and see that again, this one has a larger force, larger acceleration. That means a bigger velocity, so it can cover a bigger distance in the same amount of time. Okay, so that's it for simple harmonic motion.